Welcome to today's class of intermediate microeconomics. And today we're going to discuss a lot of theory on utility and choice, but we start from practice. So once in a while, when you go shopping on the street in the city center of Groningen, what may happen to you is that you meet a beggar, and the beggar will ask you for money. And you need to consider whether to give the person money or not. And you may be tempted to do so, but you may also consider that the person may not spend the money on the things that help him, like healthy food or a place to stay at night, but on bad things that are not in the person's self-interest, like alcohol or drugs. So you might prefer to give the person an apple or something healthy instead of just plain money. Often you don't have the opportunity to do so, and then it may also be an easy excuse not to give the person anything and not to help him. So we have something like this at large in the US, which is the food stamp program, or nowadays called the SNAP program, the Supplemental Nutrition Assistance Program, and this program is large. And what does this program entail? It gives in-kind transfers, so not money, but vouchers to the poor, and the poor can use these vouchers for food and housing, so things that are considered to help them. And they enjoy a much more political support often than cash transfers, for the specific reason that voters might think that the poor people, if they just receive cash, will not spend them on food and housing. So by giving them vouchers instead, the idea is that the poor are forced to spend them on food and housing. So, and the food stamp program is large, and does it also help? So then we turn to microeconomic theory. What does microeconomic theory says about the effectiveness of the food stamp program? And what does the empirical evidence say? Fortunately, we have empirical researchers, very fine empirical researchers, who examine this question and write a paper on this to report to us the results. Before we go to the results, first an impression how important the food stamp program, or the Supplemental Nutrition Assistance Program, is in the US. I have a graph for you about the development in the last 20 years, and you can see that in 2013, 15% of all Americans, so more than 40 million American people, were on the food stamp program. It has gone down slightly afterwards, but even in 2019, 35 million people in the US were dependent on this program. And the share of the US population participating is more than 1 out of 10. So what is the impact of the food stamp program on food spending? So what it's supposed to do? We will address this question today, because today we are going to get into the question of what is the optimal choice given the preferences that people have. So in the last lecture we dealt with preferences, and now we bring in some new elements. So we bring in prices, we bring in people's income, and then we maximize utility given people's preferences. We maximize utility given the prices and given people's income. And we also going to address this question the other way around. So given that we want to obtain a certain level of utility, what is the income that we need in order to attain that level of utility, given prices of the products? That is what we are going to do today. So what we did last time is to maximize utility. So we had the marginal rate of substitution, and the marginal rate of substitution was the derivative of the utility function with respect to good x over the derivative with respect to good y. And this rate of substitution tells us how much of one good Y a person is willing to give up in order to obtain one more unit of good X. And this is entirely driven by this person's preferences. What we're going to do today is to address the question, how much has someone to give up of good I? So how much does he have to give up of good I in order to obtain one more unit of good X? Of course, that doesn't depend on the person's preferences, but it depends on the relative prices of the goods X and Y. So market prices, they convey the information about the opportunity cost to the individuals. And it's important to realize that as long as the price ratio of the two goods is not identical to the marginal rate of substitution, then the person can usually be made better off by trading. And why do we say usually and not always? Well, it can happen that we are in a corner solution, so the individual has to decide on how many units of two goods to consume, but his preferences is, given the prevailing prices, to spend all of his income on good Y only. So he's in a corner solution. Then it can happen that in this corner solution, the marginal rate of substitution is not identical to the price ratio of the goods. He would like to even more consume more units of good Y, but hey, he already consumes his entire income on good Y, so he cannot further improve. So he can no longer trade because he already spent his entire income on good Y. That's a corner solution. If we're not in a corner solution, then a person can be made better off by trading as long as the marginal rate of substitution is not identical to the price ratio. Let's go over an example. So we consider Julia, and Julia is living in an economy where two goods are available, coffee and tea. She has an initial endowment of coffee and tea, and her initial endowment is such that she is willing to give up 4 cups of tea in order to get 1 additional cup of coffee. That means her marginal rate of substitution is equal to 4, because her marginal utility of a cup of coffee at this point is 4 times the marginal utility of an extra cup of tea. So the new element is that we now consider the prices. So let's consider the price of coffee, which is 2, and the price of tea is equal to 1. So the price ratio between the two goods is equal to 2, which means that if we answer the question, how much does Julia need to give up in order to get 1 additional unit of coffee? Well, she only needs to give up 2 cups of tea in order to get 1 additional unit of coffee. Cup of coffee. So she doesn't have to give up 4 cups of tea. So that's great for Julia, and she can increase her utility by doing exactly that. Giving up 2 cups of tea, saving her $2, and spend that $2 on an extra cup of coffee. This trade is beneficial for Julia. So now to a more formal treatment, and we consider first an economy with only 2 goods. To simplify things, we have goods X and Y, and the consumer's choice on X and Y is not unconstrained. So normally more is better. So if it's unconstrained, you would buy an infinite number of units of X and an infinite number of units of Y. But as you also find out in your daily experiences, you're constrained by your budget. So this consumer also has an income I, and she can spend it on goods X and Y. So we have a budget constraint PXX plus PYY should be less than equal than the budget. So the expenses should not exceed the income the person has. And in practice, we assume that the consumer cannot save to the next period. There are no dynamics here, no lifetime utility. So the income is completely spent on good X and Y. The constraint is binding and we have an equal sign. Graphically, we can represent this as follows. So the orange area over here is the budget set. So these are all combinations of goods X and Y that the consumer can buy given the income he or she has available. So this is the budget set, but in practice there's no saving. So the consumer will spend the entire budget, and the consumer will always choose a combination of units of X and Y that is on this line over here, and we call this line the budget line. So, and if the consumer spends the entire income on good Y, then she can buy I over PY units. So her entire income is equal to Y, I. And if the price of good Y is PY, then if she spends her entire income on that particular good, she can buy I over PY units. And the same if she spends her entire income on good X. So the budget line, this green line over here, can be represented by this equation over here. And I can do a quick derivation here. So if we have the tablet, then if we write the budget constraint as px times x plus py, y is identical to the income, then we can solve for y by writing y is equal to income over the price of good y minus pi x times x divided by pi I, and then this part here is A, and this part here, the price ratio, we write as B, and this equation reduces to one that you know from elementary math. Y is A minus B times X, and we know that this is the intercept, and B here denotes the slope. So we know that the intercept is equal to I over PY, and the slope of the budget line is equal to PX over PY. Okay, so now we know how we arrive at the equation for the budget line, with this being the intercept and this being the slope. And for interior solution, so what do we need to do? We need to equate the marginal rate of substitution to the price ratio. Now we know that the slope here of the budget line is the price ratio, so we need to find a utility function that is tangent to the budget line. So how does it work? Well, you know it from Micro 1. So more is better. So here we have a couple of indifference curves, and the utility associated with U3 is higher than the utility associated with U1 because it gives us more of X and more of Y. So if we consider this indifference curve U1, then it intersects with the budget line at point A, giving us utility level U1. But we can attain a higher utility level given that this is our budget set, because we can also reach the higher utility level U2. It's a higher indifference curve, because if we do not consume, if we don't buy the combination of X and Y represented by point A, but the combination represented by point B, then we're at indifference curve U2, giving us utility U2, which is more than U1. So we are better off. We cannot reach the combination C because our income doesn't allow that. Point C is not part of our budget set. So we would like to attain utility level U3, but we cannot because we are constrained by our income. So U2 is the maximum utility that we can reach given our budget, and we can reach this utility by consuming the combination of X and Y represented by point B, and point B is exactly the point where the indifference curve is tangent to the budget set. Or stated differently, it's the point where the marginal rate of substitution is tangent or is identical to the price ratio of good X and Y. And this is an interior solution because we are not at one of the corners where we only consume good X or good Y, but we're somewhere in the middle where we mix the consumption of A and B. So in formulas, it looks as follows. The highest feasible utility level is where the indifference curve is tangent to the budget constraint. So the negative of the price ratio, prices are positive, but this slope is negative, so that's why we have a minus sign here, should be identical to the marginal rate of substitution between X and Y. So the slope of the indifference curve where we fix the utility level at level U2. And this brings us to the familiar expression. So this thing is also negative, so we get rid of the minus signs there. Okay, so far we did not talk of any specific utility function, but of course we have some stylized utility functions that do most of the work in this course. And one of them is the Cobb-Douglas utility function. So we consider a utility function x to the power alpha, y to the power beta. Then we know that the marginal rate of substitution, taking the derivative of the utility function with respect to x and the partial derivative with respect to y, we know that the marginal rate of substitution is equal to alpha times y divided by beta times x. Then at the optimum, so at the optimal consumption bundle that we are allowed to buy given our budget, we know that the marginal rate of substitution needs to be identical to the price ratio. So we can solve this one for y, and we get that the consumption of y as a function of the consumption of x is equal to beta px times x divided by alpha over pi. So yeah, I can also show that. So let's do it like this. So we have that the marginal rate of substitution x, y at the optimum needs to be equal to the price ratio px over py. Then we replace the marginal rate of substitution by the expression alpha y over beta x over equal to px over py, and then we can bring this to the denominator and this one to the numerator, and we arrive at the blue expression that we have over here. Or now I should that we have over here. So this is in blue because we're going to use it. We are going to insert, we're going to replace y in the budget constraint for by this expression over here. Because we know that in the optimum we are at the budget set. So we spent our entire budget. So at the optimal point we spend our entire budget, and it needs to hold that y as a function of x has the following form. So we replace the y in the budget set by this expression. And now we have one equation and one unknown, and the one unknown is our consumption of x. So we can rewrite this a little bit in order to solve for x, and we find that at the optimal point, our consumption of x, the number of units that we consume, is identical to alpha times our income divided by the price of good x. And then, of course, you can insert this into the equation that we have over here, and you find the solution for the optimal consumption of good y, which is equal to beta times income divided by pi units. And this expression is very particular to Cobb-Douglas. So if we keep in mind this expression for x over here, then and let me repeat it for convenience. So for Cobb-Douglas, the optimal consumption of good x is alpha times income divided by px. And of course we can rewrite this by bringing the px to the left-hand side of the equation, and we get that the price of good x times the number of units that we buy in equilibrium is equal to a share alpha of our income. So in other words, well, if I buy x star units of good x and the price of each unit is px, then the left-hand side of this equation denotes my total expenses on good, and sorry for the handwriting, but the left-hand side denotes the total expenses that I do on good x in equilibrium, and these total expenses are identical to a share alpha of my total income. And that's very specific to the Cobb-Douglas utility function. Another thing to notice is that in this expression for x star, it depends on income. It depends on the price of good x in a very natural way. So if my income increases, I will buy more units of good x. Yeah? So if my income goes up, then my consumption of good x will go up as well. And the relation with price is also very natural, because it implies that if the price of good x goes up, then the number of units of good x that I will consume in equilibrium will go down. Importantly, the expression does not depend on the price of good y. So if the price of good y changes, either it increases or decreases, nothing will happen to my optimal consumption of good x. I will always consume the same number of units, independent of the price of good y. And this is because I will always spend a fraction alpha I of my income on good x. So if my income doesn't change, that fraction will stay the same, or that amount will stay the same, so my total expenses on good x will stay the same. So if my income doesn't change and the price of good x doesn't change, my optimal consumption of good x will never change. That is for the Cobb-Douglas utility function. Now, graphically, it looks as follows. So the Cobb-Douglas utility function brings you to an interior solution, and the optimal consumption of good x and y are as follows. And then we can take the ratio of these two expressions, and if we divide beta I over py by alpha I over px, then the income levels y, they drop out, and a ratio in which we consume good x and good y in equilibrium depend on the price ratio of good X and good Y. So what we observe here is that the ratio in which we consume good X and good Y, given the Cobb-Douglas function, does not depend on income, because the income doesn't appear in the right-hand side here. And it does depend on the relative prices of good X and good Y. So it depends on the price ratio of good X and Y. What does that mean? That it doesn't depend on income, but only on the price ratio. It means that the Cobb-Douglas function is homothetic. So, and I think that will be in the next one. Yeah, so now suppose that our income increases. So we used to have an income of Y. Now our income gets topped up with delta. So our new income is equal to I plus delta. So it means that if we spend this entire new income on good Y, we cannot buy I over PY, but we can buy I plus delta over PY units of Y. Same if we spend our entire income on good X, we can now buy I plus delta over PX units of good X. So, difficult way of saying that our income, our budget budget line shifts to the right. In a parallel fashion, because the price ratio, the prices of good X and Y didn't change, so the relative prices of good X and Y didn't change, meaning that the slope of the budget line stays the same as before. So this slope of our new budget line is the same slope as in the old budget line, but it has shifted to the right. Now, given that we have a Cobb-Douglas utility function, which is homothetic, it means that the ratio in which we consume X and Y in equilibrium doesn't depend on income, but only on the price ratio. The price ratio didn't change because the slope of the budget line is the same as before. So it means that we increase our consumption of X and Y in proportion. So the ratio at the optimum in which we consume X and Y doesn't change, which means that we move from the optimal point B to the new optimal point B prime, given our new income level. Because B prime is the only point at the new budget line in which the ratio in which good X and Y are consumed is identical as in the old optimum B. And, well, you can just replace the income in the old expression by the new income, I plus delta, and you get the new consumption levels. And all that follows from the bare fact that the Cobb-Douglas function is a homothetic utility function. Okay, so final thoughts on this example. So we have a Cobb-Douglas utility function. It is rather limited in its ability to explain actual consumption behavior, because if you realize this, you also see the limitations of the Cobb-Douglas utility function. Because imagine we have two goods X and Y, say tea and coffee, and you start out with a certain income. Now your income doubles. Will you consume tea and coffee in the same ratio, or will there be a shift towards one or the other? It may be that if you get a really nice income, you will spend more on coffee, buying some more coffee and less tea, because, well, coffee is normally a bit more expensive. It's a luxury product. So you might change your ratio in which you consume coffee and tea. The Cobb-Douglas function doesn't allow you to do that. So it fixes the price, or it fixes the ratio in which you consume good X and good Y. And that's quite a limitation. Because the share of income devoted to a good often does change when economic conditions change, and then you might want to have a more general function that accommodates for that. So another question is, does the tangency condition necessarily need to hold at the optimal choice, given that we assumed monotonicity? No, it holds in most cases, but not in all. So to see some cases in which it doesn't hold, and I already referred to that at the beginning of the lecture, is one exception is when you have perfect substitutes. So if two goods are perfect substitutes, then you have a linear utility function, and the marginal rate of substitution between the two goods is equal to alpha over beta. And we arrive at a corner solution where only one of the goods is consumed, because we have straight utility or straight indifference curves. So, and the budget line is similar as before, but now we have straight indifference curves described by this utility function over here. The slope of this indifference curve depends on how we choose our constants alpha and beta. But either the slope of the indifference curve is steeper than the slope of the budget line, or this slope is more shallow. Now, this is a situation where the slope of the indifference curve is steeper, meaning that we are willing to give up a lot of units of y in order to get slightly more units of x. So our preferences really favor good x. This is what this steep indifference curve means. If we look at the budget line, okay, we need to give up units of y in order to get more units of x, but the price ratio is more favorable towards consuming more units of x. So we need to give up some y, but we can get a reasonable amount of x for that. Now, if this is your indifference curve, if this indifference curve describes your preferences, you are willing to give up a lot of y in order to get a little more of x, yeah, then you can increase your utility by not consuming good x or not consuming good y at all, and consuming the consumption bundle that's exactly here. You spend your entire income on good x. So you maximize your utility at point A, then you reach a utility level U3, which is more than U2 and U1. And also at this point, it still holds that the marginal rate of substitution given by your indifference curve, the slope of the indifference curve in absolute value, is still larger than the price ratio of good x and y, which is given by the two prices and the budget line. So this is one exemption to the tangency rule. A second exemption is when the goods are not perfect substitutes but perfect complements. So you get these hooked indifference curves. So in the case of perfect complements, your utility function looks as follows. Your utility is identical to the minimum of alpha times x and beta times y. And your marginal rate of substitution is either 0, infinity, or undefined. So here the slope is equal to infinity. So you're willing to give up a lot of y to get a very small amount extra of x, or actually none. So it's really a limiting value. And at point A, then it's undefined. So at point A, you have this kink, and the derivative of the indifference curve is not defined at point A. And here, the slope of the indifference curve is identical to 0. It's perfectly horizontally flat. So no matter what the prices are, the optimal rule is that you choose x and y such that alpha times x is exactly identical to beta times y. Because, well, if one is larger than the other, it pays off to reduce the one in order to get a little bit more of the other, because your utility is defined by the minimum of the two. So here we're not in a corner solution, so we don't spend our entire income on only x or y. But if this brown curve is our budget line, and the slope of this line is given by the price ratio, which has a certain negative value, then at the optimum consumption bundle, the marginal rate of substitution is not identical, or the slope of this budget line is not identical to the slope of the indifference curve, because the derivative of the indifference curve is undefined here. And then we arrive at the question. So the question is, does the tangency condition have to hold at an optimal choice, given that we assumed monotonicity? And I leave that question for you to answer. Let's start by answering the quiz question. Does the tangency condition have to hold at an optimal price, given that we assume monotonicity? And the answer to this question is no. It does not necessarily need to hold. And I will give you some examples. It will hold in most cases, but one case where it doesn't hold is when we reach a corner solution. And when do we reach the corner solution? Now, for example, when the indifference curves are not strictly convex. So in the case of perfect substitutes, we have straight indifference curves that are convex, but they are not strictly convex. And this is a situation where we may end up at a corner solution. So in the case where the tangency condition doesn't hold. The tangency condition does hold when we have strictly convex preferences. For example, as when we assume the Cobb-Douglas function, and we have a diminishing marginal rate of substitution, and we reach an interior optimal solution. In those cases, the tangency condition will hold. Some good news, what is always true, that if we have an optimal point, then it needs to be a point where the indifference curves do not cross the budget line. So in any optimum, the indifference curves will never cross the budget line. Okay, so now we are ready to move from the two good case to the economy with n goods. So now the consumer has a choice between n goods when he wants to spend his or her budget. So the utility function is now a function of the consumption of all n goods, and the same holds for the budget constraint. Again, we solve for the optimal consumption bundle, and in order to do this, we now set up the Lagrangian, and often this is asked of you to do as well. Solve for the optimal solution by setting up and solving the Lagrangian function. So the Lagrangian function has the following form. So it's this curly L equal to the thing that we want to optimize, in this case the consumer's utility, and then within parentheses we write the constraint that needs to hold. So the thing within parentheses in our optimum needs to be identical to 0. And as you can see here, the thing that we have within parentheses in this case is our budget constraint. So if this part is equal to 0, it means that we completely deplete our income by spending it on consumption of goods n1 to n. And this is the Lagrangian parameter lambda. And we solve for the Lagrangian by taking the first order conditions with respect to all consumption goods and with respect to lambda. Now, what does it look like? In general form, the n plus 1 first order conditions take the following form. We take the partial derivative of the Lagrangian with respect to good 1. gives us the partial derivative of the utility function with respect to good 1 minus lambda times P1. So, and this originates from differentiating this part with respect to x1, which leaves us with minus lambda times P1. That's the thing over here. And at the optimum, this first order condition needs to be identical to 0. Now we do the same for goods 2 to n, and this gives us the first n first order conditions that need to hold at the optimal solution. And then we have one more, so we also differentiate the Lagrangian with respect to lambda. So differentiating this thing with respect to lambda gives us I minus P1 x1 minus P2 x2 and so forth. And this needs to be identical to 0 in equilibrium as well. And you notice that this is just saying that the budget constraint needs to be satisfied in equilibrium. So that's the n plus 1th condition. So in equilibrium, at an optimal solution, all n plus 1 conditions need to be satisfied. Now, in solving this system of first order equations means that we need to find the x1, x2, xn and the value of lambda that satisfy jointly these n plus 1 conditions. So what do we learn from these first order conditions? Now, we focus first on these ones over here. So take one of the goods, good I, then the first order condition for that good is that the partial derivative with respect to xy minus lambda pi needs to be 0 in equilibrium. And this needs to hold for all goods 1 to n. So take two goods, I and j, then we have two of these conditions, and they take the following form. So let's switch to the tablet. So we have, we take the Lagrangian derivative with respect to xy, gives us this condition over here. Now we have switched the lambda pi to the right hand side of the equation, gives us this expression over here. We can do the same for good j, gives us the expression over here. These two conditions need to hold at the optimal solution. And what we now can do is we can divide this equation by this one, both the left hand side and the right hand side. Now doing the division for the left hand side gives us this partial derivative over this one, which we now have here. And doing the division also for the right hand side of the equation gives us lambda over pi, or lambda pi over lambda times pj. And we have lambda both in the numerator and the denominator, so they cancel out. And we are left with pi over pj. And this, of course, is the familiar condition, because it says that at the optimal solution, the marginal rate of substitution, which is the thing on the left hand side, the marginal rate of substitution between good x and good j, or good I and good j, needs to be identical to the price ratio of the two goods I and j. That's one thing that we learn. And a second thing that we learn is that we can rewrite this expression, for example, for good y, and solve for lambda, and that gives us an expression of lambda. Lambda is equal to the derivative of the utility function with respect to xi over the price of good I. So far for the derivation. So now I return to the slides, where we have the same thing. So by definition, that is what the three horizontal bars here mean. By definition, the marginal rate of substitution between good x, I, and j is equal to the partial derivative of the utility function 2xi over the partial derivative with respect to good j needs to be identical to the price ratio in equilibrium. Which means that the personal trade-off, this is the trade-off for the individual that we consider, needs to equal the market trade-off. So the prevailing prices of good x and j. And we also have that lambda is equal to the partial derivative of the utility function with respect to good 1 over the price of good 1. And we did it in our tablet for good I, but we could do it for all goods. So this needs to be identical for all goods and be equal to lambda. That means at the equilibrium solution. So how to interpret lambda? Now, lambda is the marginal utility of income at the optimum, at the optimal solution. So it's equal to the marginal utility to marginal cost ratio of each good. So how can we see this? Now, suppose that good 1 is cups of coffee and that the additional utility that we would receive from buying an additional cup of coffee is 4. But that the price of a cup of coffee is 2. That means that if we have 1 additional unit of income, that would allow us to buy half of a cup of coffee, not an entire cup of coffee. Now the marginal utility of an extra cup of coffee is equal to 4. So the marginal utility of half of an extra cup of coffee is equal to 2. So if we have 1 more unit of income, that would allow us to buy half a cup of coffee, and so to increase our utility by 2. So the marginal utility of 1 additional unit of income is equal to 2. And this is a bit of magic. So this implies that no matter how we spend an extra euro of income, whether we spend it on coffee, tea, or shoes, our increase in utility will be the same, because the marginal, if we spend our extra income on coffee, the increase in utility will be the same as when we would spend it on tea or extra units of shoes. And this is because we consider the optimal solution. So once we have optimized everything, we have optimized our consumption of coffee, tea, and shoes, then if we would receive an extra unit of income, the model predicts that it doesn't matter on which good we spend this additional unit of income, our increase in utility would be the same. So we can also rewrite it differently. So we can now also solve for the prices. So it means that the price of a good, the market price, is identical to the individual's willingness to pay for the last unit of the good. So let's do an example. Suppose that 1 extra unit of good X, say coffee, would increase our utility by 6, and 1 extra of income would increase our utility by 3. So the derivative of the utility function with respect to X is equal to 6. And lambda, the marginal utility of income, is equal to 3. So then dividing the 2 means dividing 6 by 3 is equal to 2. So 2 extra units of income would provide you with the same increase in utility as 1 extra unit of X, because we know 1 extra unit of income would increase our utility by 3, so giving us 2 extra units of income would increase our utility by 6. But we could also increase our utility by buying 1 extra good of X, because that would also increase our utility by 6. So it means that we are indifferent between getting in kind 1 extra unit of X or 2 extra units of income. So it means that in equilibrium, the price of good X needs to be equal to 2, because then we're completely indifferent between getting an extra unit of good X or getting 2 extra units of income. So one caveat here, this analysis only works if we are at an interior optimal solution. So for example, if goods are perfect substitutes, we will still obtain a corner solution where only one of the end goods will be bought. Same holds if we have perfect complements, then our utility function in general form will look as follows, where the alphas are constant, and the optimal consumption bundle is given by the following chain of equalities. At the optimum, we will consume the number of units of good 1, 2 till n, such that this equation holds. So importantly, if you are asked to solve for the optimal consumption bundle in an n-good economy, if you have a utility function that allows for an interior solution, then you can use the Lagrangian and solve it. If you have a situation where you have a utility function that represents perfect substitutes or a situation of perfect complements, then solving the Lagrangian will not get you anywhere, but you need to use equalities like this one, or realize that only one of the goods will be bought in equilibrium. We focused on first order conditions. There's also something like second order conditions, and solving the first order conditions is sufficient for finding the constraint maximum, so finding the optimal consumption, as long as the objective function, the thing that we want to maximize, in this case the utility function, is what is called quasi-concave. Now for the two-good case, if we have only goods x and y, then quasi-concavity is satisfied as long as the indifference curves are convex. So just as a quick reminder, what does this mean? So an indifference curve is convex if you take 2 points at the indifference curve. So this is the two-good case. So we take two consumption bundles on this indifference curve. We draw a straight line between these 2 points, and all the points on this straight line also give you a utility level that is at least equal to the utility level U bar. So every point connecting the two on the line that connects the 2 points on the indifference curves gives you a utility that is at least as large as U bar. Then we have a convex indifference curve. So what is an example of an indifference curve that is not convex in two-good case? That's an indifference curve like this one over here. If we take two dots on the indifference curve, say this one and this one, we draw a straight line between the two, then we have points at this line, for example this one over here, that give you a utility level that is strictly less than U bar. For example, this one would be on a lower indifference curve that would look something like this. Okay, so that is for the two-good case, but I have another piece of good news for you, because in the higher order cases in this course, if you are given a utility function, you can rest assured that that utility function that is given to you is quasi-concave. So you don't have to check this, you don't have to check the first or the second order conditions, you only need to check the first order conditions. And if you do that, you take for granted that the second order conditions are also satisfied, and we have reached a maximum utility level. Okay, so let's move on to the demand functions. So we have a system of first order conditions, n plus 1, that follows from the optimization problem, and we can solve for the optimal values of x1 to xn, which gives us the optimal consumption bundle given the prevailing prices and given our income. So what we then get is a system of what are called uncompensated or Marshallian demand functions. So uncompensated refers to what is the nature of these demand functions, and Marshallian refers to Alfred Marshall who has given his name to these demand functions. But so we have two names for the same thing. And the optimal consumption bundle x1 star to xn star is then a function of the prices of the different goods and our income I. So we have an uncompensated demand function if it's a function of the prices and income. And now I will ask you to study examples 4.1 and 4.2 of the book. So the demand functions have some properties, and so what they do is they give you the utility maximizing consumption level of a good given prices and income. And one property of demand functions is that they are homogeneous of degree 0. So what does that mean? It means that if we multiply prices and income by a common factor t, then our optimal consumption will not change. So it means, for example, if you have inflation, and inflation is 10%, then t is equal to 1.1. But if prices increase by 10%, but at the same time your income also increases by 10%, then in fact your purchasing power didn't change. Prices have become higher, but your income increased as well. So you can buy the same consumption bundles as before. So the budget set, the orange triangle, is exactly the same as before. So you have no reason to change your optimal consumption bundle. So meaning that if we multiply prices and income by the common factor t, it doesn't have any impact on our optimal consumption bundle. So we can use also the uncompensated demand functions to arrive at something that is called the indirect utility function. So the direct utility function that we considered so far is a function of our consumption bundle. And the consumption bundle, what we consume, that gives us a direct utility. But if we replace the consumption bundles, the optimal consumption bundles, in the direct utility function by the expression that we have obtained, so the Marshallian demand functions, so we replace in the utility function the consumption bundles by the expressions that are a function of prices and income, then we end up with a functional form that is a function of prices and income. Now, a price or your income doesn't give you direct utility, but your income gives you indirect utility because you can convert your income into a consumption bundle, which gives you utility. So the indirect utility function is a function of prices in income that do not give you direct utility, but the consumption that your income allows you to buy does give you direct utility. And this is often very handy because now we don't need to worry about the actual consumption bundle that an individual buys. We only need to consider prices, and we can change the prices. And the indirect utility function exactly tells us how an individual's utility will change if the prices of one of the goods changes or if the income changes. And we can be agnostic about how exactly the individual solves his optimal consumption bundle problem. Okay, so this is what I just stated, and let's go through a practical example here to make things very precise. So what we do is we study the impact that the introduction of a tax has on the level of well-being, meaning utility, using the concept of indirect utility. So, for example, suppose that a candidate for the US presidential elections promises to cut back income taxes. And this is what they often do. But in order to balance the budget of the government, the candidate also proposes to raise taxes on consumption goods. So the policy proposal is what is called budget neutral. Is this a sensible policy? In the sense, is this a policy that increases individual well-being? Well, let's have a look at that. So we take a specific utility function, we take a Cobb-Douglas utility function, we limit ourselves to a two-good economy with only good x and good y, and we assume that the parameters of the Cobb-Douglas function, alpha and beta, are equal to 0.5. Now remember from the first part of this lecture that at the optimum, the individual, given that alpha and beta are both equal to 0.5, the individual will spend half of his income on good x. So given that the price of good x is px, that will allow him or her to buy 0.5 I over px units of good x in equilibrium. And at the optimal point, this individual will also spend the other half of his income on buying units of good y. So this is, here we have our optimal consumption of good x and good y as a function of prices and income. So these are the uncompensated Marshallian demand functions. And what we now can do is to plug in these expressions into the Cobb-Douglas utility function. So we replace the x and the y in the Cobb-Douglas utility function by the expressions that we have over here. So I already done that here. We simplify a little bit and we arrive at the following expression. Now here, this is a function only of prices and income, and this then is our indirect utility function. So it directly translates, given that we have an income y and that the prevailing prices of good x and y are px and py, then at the optimum our utility level will be equal to this expression over here. So let's plug in some numbers. Suppose that initially the prices of good x and good y are both 1 and that the individual's income is equal to 8. So then plugging in 1, 1 and 8 in this expression over here, we obtain that the initial utility is equal to 4. And we can also solve for the optimal consumption bundles, and we observe that the individual total income is 8. He will spend half of his income on good x. The price of good x is equal to 1. So at the optimal point, he will buy 4 units of good x. Now we introduce a tax and we levy this tax on good x. So, and we levy a tax of 3, t is equal to 3 on good x. So the after-tax price, after the tax is has been imposed, the price of good x rises to 4. Original price was equal to 1. We add a tax equal to 3, so the after-tax price is equal to 4. Given that we have a Cobb-Douglas function, again, we will spend, also given the new prices, we will spend half of our income on good x. Our income didn't change, it's still equal to 8, but the price of good x did change. It's now equal to 4. So we spent half of our income, meaning 4, on the consumption of good x, but 4 units of income only allow us to buy 1 unit of x. So in the new optimum, we will consume 1 unit of x. On this unit, we need to pay a tax equal to 3. So the government revenue of introducing the tax is equal to 3 times 1 is 3. Okay, so this is when we impose the tax, and this is bad for the person's utility. As most taxes are, indirect utility will fall to 2. So we can immediately see that from plugging in the new price and the old price for good y plus income in this expression over here, because we have 8 divided by 2 times 4 to the power 0.5, which is 2 as well, times 1. So we divide 8 by 2 times 2 is 4. 8 divided by 4 is equal to 2. So the indirect utility of this individual, because of the introduction of the tax, will fall from 4 to 2. And now let's do the comparison. So suppose now that we will not, no, the policy needs to be budget neutral. So let's suppose that we raise the tax, but we want to raise the same amount for the government, but we do not do it by imposing an extra tax on good X, but by increasing an income tax. So we just take the 3 immediately from the individual's income. Now then, if we have this income tax, the individual's income will reduce by 3. So he will be left with 5 units of income. And in this situation, we don't impose a tax on good X because we have an income tax. And so the prices of good X and Y stay at their original level. Okay, so now the individual needs to optimize again, given his lower income. He will spend still half of this lower income on good X. The price of good X is equal to 1, so he will buy in the new equilibrium 2.5 units of good X and also 2.5 units of good Y. And the indirect utility of this individual now fall to 2.5. We can see that by plugging in the numbers. Our income is now equal to 5, prices stayed at the old level, and solving we get that the indirect utility is 2.5. Importantly, the indirect utility is now higher than if we would not have an income tax, but instead have imposed this tax of 3 on good X, because in that case our indirect utility would have been reduced to 2. So what we find is that if you want to generate revenue as a government, it's better, it's less bad for individual well-being if you tax people's income instead of levying a tax on individual consumption goods. So then the question is, why is that the case? Now let me give you a graphical exposition here, which shows you the idea that if you impose a tax on a specific consumption good, then it will distort an individual's consumption choices because he will substitute away from the tax good. We observe that initially the consumer was consuming 4 units of good X and good Y, but then the price of good X increased from 1 to 4. That made the individual substitute away from good X towards consuming more of good Y. And that is the distortive effect of taxes. Now to see it in pictures, in the original situation, price of good X and good Y is equal to 1. So the slope of the budget line is equal to -1. We have an optimal level of consumption at the point over here, allows us to reach the utility level U. And now we increase the price of good X by imposing a tax on good X. So if the price of good X increases, it means that the budget line pivots around the intersection with the Y-axis. If we would still spend our entire income on good Y, then we could still buy the same number of units of consumption as before because the price of good Y didn't change. But if we spend all of our income on good X, yes, then we can buy less units than before because the price of good X has increased. So the budget line shifts inwards and the price ratio of good X and Y has changed. The budget line, the slope has become steeper. Well, given the new prices, given the tax on good X, the best the individual can do is to re-optimize, to substitute away from consuming good X. So he reduces the consumption of good X from X star to X1. And at the same time, he somewhat increases its consumption of good Y from I star to Y1. So at the old situation, optimal consumption bundle is X star, Y star, completely depleted the income. And in the new situation, the new price of good X is 1 plus T. And we can rewrite it as follows. And we do this because Tx1 is the revenue to the government, the number of units of X that is consumed in the new situation, times the tax imposed on the good. And we can rewrite it as follows. So this is just rewriting the budget constraint in the first step. And what we do in the second step is to replace the income here by the expression X star plus Y star. So that allows us to get rid of the income here, and we instead have X star and Y star in the expression to the right. Now, why do we do this? I do this because this shows you that the tax revenue to the government is equal to the change in the consumption of good X. So it's equal to this part on the horizontal line. So the change in the consumption of good X plus the change in consumption of good Y. So, but notice that it's Y star minus Y1, and Y star is less than Y1. So this is a negative term. And this one is positive because initially we consumed more units of good X than in the new situation. Now, because we assumed, and this is very special to the situation that we have here, because we have assumed that the prices of good X and good Y are 1 at the initial situation, so the slope of this indifference curve, or the slope of the budget line, is equal to minus 1. Because of that, it means that the size of this line, this difference between I1 and Y star, is exactly identical to this line over here, between this dot and where the two dotted lines cross. So it means that the revenues of the tax to the government are graphically identical to the difference between X star minus X1 minus this line over here, which is identical to this part. So the net revenues to the government are equal to this this part of the y-axis. So these are the government revenues. Why do I represent it like this? Well, now we can also graphically show you an equivalent change in income tax that would give the government the same revenue. So this is what happens if we impose a tax on good X. But now, if we want to obtain the same revenues by imposing an income tax, then we need to reduce income by this amount over here, such that we are at the green line. So this is the revenue equivalent income tax. And what then, given this income tax, what is the optimal consumption bundle of the individual? And now it's important to note that if we do the income tax, then it's possible for the individual to choose the consumption bundle X1, Y1 as the consumption bundle of choice. So if instead of imposing a tax on good X, we would do an income tax, then the optimal choice under the good specific tax would be still available to the individual. And why is that? Well, we have reduced the income by the tax and both prices are still equal to 1. So we reduce the income by the T times X1. And we know that it needs to hold that this is equal to X1 plus Y1, because that's here on the left-hand side. So if we reduce our income by Tx X1 and the prices of good X and Y are still equal to 1, then we can spend just this remaining budget on good X and good Y, and we are able to obtain this consumption bundle. That's feasible. However, the individual can do better. So the indifference curve U1 that runs through X1, Y1 is not the highest indifference curve that this individual can reach, given that his budget line is equal to the green line over here. He can reach a higher indifference curve by consuming X1 prime, I1 prime. And this is just graphically showing that a revenue equivalent income tax allows individuals to reach a higher indifference curve than a tax on a specific good if we are at an interior solution. So if we have convex indifference curves that allow the individual to substitute away from the good that is taxed. So to summarize, individual reaches a higher level of utility when a tax is collected as a lump sum tax instead of a good-specific tax. And this is because the lump sum tax do not distort choices. Consumers do not substitute away from the good that is taxed. And so the individual can reach a higher indifference curve if she gets a lump sum cash transfer instead of a subsidy on the price of a specific good. So, as you know from previous micro courses, a subsidy is just a negative tax. So, we have shown that an income tax works better than a good specific tax. And similarly, if you give people just money, if you increase their income, they are able to reach a higher level of utility than if you would spend the same amount on giving a subsidy on a specific good. So income supplements are welfare improving more than an equivalent subsidy on a specific good. This, of course, is a very nice bridge to return to the empirical study at the beginning of the lecture. But before we do that, we have another quiz question. So the quiz question is, for demand functions, we have that x, y, and these are uncompensated Marshallian demand functions because they're a function of price and income. We have that if we multiply prices and income with a factor t, then it's equivalent than multiplying the original or the Marshallian demand functions at the initial prices and income by a factor t to the power a. And then which value does a have? That's the question. And this is the question for you to answer. And the answer to our quiz question is that a should be equal to 0, because Marshallian demand functions are homogeneous of degree 0. If we increase or multiply prices and income with a common factor, then the optimal consumption bundle will not change. And then we continue with the empirical study by Hoynes and Schanzenbach. So far we compared lump sum solutions to price changing solutions, and now what is done in this study out of 2009, 2 lump sum transfers are compared, 1 cash transfer and 1 in-kind food stamp transfer. And as said at the beginning of the lecture, many voters believe that it's better to give people vouchers that allow them to consume specific goods, like food, for example, instead of giving them just cash, which also may allow them to buy bags. What does microeconomic theory say? What does empirics say? Let's go into that now. So this is a picture from the study, and it shows you what happens if you introduce a food stamps program. So initially, the budget line of the consumers is equal to this line over here, and we have 2 consumers with the same budget line, and one of them chooses the optimal consumption bundle A0, and the other one chooses the optimal bundle B0. When the food stamp program is introduced, it means that you get vouchers that allow you to buy food, but you cannot spend them on anything else. So, for example, if you would already consume your entire income on food items, then you would now be able to buy even more food items. So the budget line shifts outward here. But you can see that this gray triangle is a point or are consumption bundles that cannot be reached with the food stamp program. But this region could be reached if you would do an equivalent cash transfer, because then the entire budget line would shift to the right. But with the food stamp program, we have a kink in the budget line because, for example, if you would spend nothing on food and you would spend all of your income on other goods, say alcohol, then now you get food stamps, but you cannot use the food stamps to increase your consumption of alcohol even further, because the food stamps can only be exchanged for food. So the only thing that you can do is to buy the same amount of alcohol that you did before, and in addition spend the food stamps on food. So people who are at this point over here, who didn't buy a lot of food beforehand, because of the food stamp program, they will probably increase their consumption of food. And this is of course what the program intends to do. However, for the consumers who are without a food stamp program at an interior solution, like the one who consumes consumption bundle A0, for them the impact of the food stamp program is different. Because suppose that the size of the food stamp program is equal to capital BF, so it allows you to spend this amount extra on food, to consume that many extra units of food. What will happen is that, these people already bought food, now they receive food stamps and saying, okay, now usually I would spend cash on buying food, but given that I now have the food stamps, I will use them to buy the food items. And that will save me some other cash that I now can spend on other items, for example, alcohol. So for the people at the interior solution, it doesn't matter that much whether they receive the money in food stamps or in terms of cash. So the hypothesis of the paper are that the food bought with food stamps will increase. So that's only natural. If you have food stamps, you should use them. But families who are constrained, who consume at the kink, they will experience larger increases in the food consumption than the so-called inframarginal households who already spend money on food and non-food items. So in the picture, these households will increase their food consumption from F0 to F1. And this increase in consumption will be covered by the food stamps. They will also pay some of their initial consumption on food now by food stamps, which will leave them with some cash to spend on non-food items. So this is saying that the cash outlays for food at home should decrease. So the inframarginal households, for example, they spend $200 a month on food. Now they receive $100 in food stamps, vouchers. They will use those vouchers to buy $100 worth of food. Maybe the total food consumption will increase to $250, but whereas they used to spend $200 in cash on food, now they will only spend $150 in cash on food. So the cash outlays for food at home will decrease. Now, why do I say food at home? Because the food stamp program only allows you to buy food that you consume at home. So you cannot use the stamps to go out for dinner, which of course makes sense. So what did previous findings study? Because Hoynes and Schanzenbach were not the first to study the impacts of this program. Previous studies found that food stamps, the marginal propensity to consume out of food stamps is 4 times to 10 times higher than it is out of cash income. So in other words, if you would give people $100 worth of food stamps, they would maybe increase the total consumption on food by $50, whereas if you would give them an equivalent amount of cash, $100, they only would increase their spending on food by $5 to $15. So previous studies found that the food stamp program is very successful in increasing household expenditures on food. However, these previous studies, they compared households who were in the food stamp program, who participated in the food stamp program, to other households that were eligible for the food stamp program because they also had a low income, but who did not participate. And that leads to potential selection bias, because you can imagine that eligible households who do not participate in the food stamp program have reasons, unobserved by the researcher, for not choosing not to participate in the food stamp program. So, and also people who choose to participate in the food stamp program, they apparently have a strong preference for participating in the food stamp program. So, and if you compare the eligible households who are non-participants with the eligible households who do participate, because of these unobserved variables, you may find that the households that are on the food program who are participating have higher food expenditures. And this may be purely driven that for unobserved reasons, these households were more eager to participate in the program. So Heinz and Schanzenbach, they do it differently. So they have a wealth of data from spanning several decades. And what they use is that in the US, it's one country, but 50 states. And the nice thing is that different states have different policies and introduce the food stamp program in different years. And they look at counties, so even smaller units. And as you can see in the figure here, more and more counties in the US started to adopt the food stamp program, especially between 1964 and 1975. The percentage of counties that had a food stamp program increased from less than 10% to almost 100%. And this allows the authors to compare counties that in a given year had a food stamp program and households in those counties with the food expenditures of households in counties that did not have a food stamp program. And of course, as long as the food stamp program does not give you an incentive as a household to switch from one county to the next, which is a reasonable assumption that you don't move because of the food stamp program, then the introduction is relatively exogenous and you don't suffer from the self-selection problems that previous studies suffered from. Okay, so that being said, what do Heinz and Schanzenbach find? They find that the introduction of a food stamp program in a county leads to an increase in the food stamp receipt. So the program is noticed and people pick it up, they start participating. Also, it helps to increase total food spending. So the food items that people buy either with cash or by the vouchers of the food stamp program. But different from previous studies, they find no significant result of the food stamp program on the propensity to spend more on food expenditures or the propensity to eat out. So the marginal propensity to consume, the MPC, for food out of food stamp income is equal to 0.16. So it means that every dollar worth of food stamps that you give to a household, of every dollar they spend 16 cents in addition on food. And the other 84 cents is substitution. So previously they already bought the food, but they paid with cash. Now they start buying by means of the food stamp voucher. And if you would give these households an equivalent amount of money in cash, then if they each additional dollar in cash, they would spend 9 cents more on food. So that's a somewhat smaller number. It seems that there's some difference that if you give the $1 in the form of a food stamp the increase in food spending is higher than if you would give an equivalent amount of cash. However, if you do some statistical tests, then these differences turn out to be insignificant. Differences were already small, but they're also not significant, and this is really different from previous studies that found that the difference between the marginal propensity to consume is 4 to 10. And this shows you how, well, the concepts that we used in this lecture are used actively in empirical work to evaluate really important policy programs. Okay, finally, we will turn to expenditure minimization. So suppose that the government has the following question. It wants to know what the minimum income level is that people need in order to attain a certain level of well-being. And well-being, again, meaning attaining a certain utility level. So what the government then can do, in principle, is to make use of the what is called the dual of the primary utilization maximization problem, being the expenditure minimization problem. And it's very analogous to the primal optimization problem, only that now the objectives and the constraints are reversed. So whereas we used to have a given income, given prices, and given that we wanted to maximize our utility, we now assume that we want to reach a given utility level. That's the constraint we impose, and we ask what is the minimum level of income, what's the minimal budget that we need in order to attain that given utility level. So let's do that, but in order to motivate you a bit more, we first need to answer the question, okay, what's the purpose of doing that? We already had the utility maximization problem. Why then also learn about expenditure minimization? That's a good question, which we're going to answer. So if we have an expenditure function E, which is a function of the price factor P1, P2, 2, Pn, and the utility level U, which is a constant that we want to attain, knowing this expenditure function will help us to analyze any impact of price changes on well-being, because it helps us to decompose the effect of such a price change into an income effect and a substitution effect. Now that's pretty abstract. A little bit more concrete is that the expenditure functions plays an important role in welfare economics. So if the government imposes a tax, as we have seen in the example that we discussed before, it leads to a decrease in utility, but utility is not very tangible. So if utility decreases by 2, it's not really clear what we mean in practice, because it depends on which utility function we choose to represent the preferences. And the expenditure function is much more helpful here, because it allows us to measure the welfare change in dollars. So it's able to translate a change in utility to a change in dollars. Because we fix the utility level at a certain level, say U bar, then we change the price, then we get a change in the expenditure function, and it answers how much extra money do we need in order to attain the same utility level as we started out with. And how much extra money people need in order to compensate them for a change in, say, taxes, is something that's very useful and practical for the government to know. Graphically, it works as follows. Now the utility level is given. So the utility level, suppose that we want to attain utility level U1, represented by this blue indifference curve. What are the minimal expenditures that we need to make in order to attain that utility level? Now, one answer would be expenditures equal to E3, which is represented by the budget line, the red budget line over here. But it's clear that this is too much, because we can reach even a higher indifference curve than the given indifference curve U1. Now, we can do with less money, can we do with only having income E1. No, that's not possible, because if we're on this budget line, we cannot reach the given utility level U1, because it's below the blue indifference curve. Turns out that the minimum expenditures that we need are identical to the level E2, which gives us a budget line that's exactly tangent to the indifference curve, which corresponds to the utility level U1 that we want to obtain. So we reach the same optimal bundle as under the primary problem of utility maximization, but we've just reversed the objective function and the constraints. Now let's push this a little bit further. So we are now interested in minimizing the expenditures, E. So it's again the sum of the amount of money that we spend on good 1, good 2 to good n, that yields a certain utility level U bar. We can again set up the Lagrangian for this problem. So now our objective function is the expenditures, and the condition that needs to be satisfied is that we need to choose our consumption bundle x1 to xn such that we reach the utility level U bar. So the thing within parentheses should be 0 in equilibrium. And now the optimal amounts, the optimal consumption bundle, will depend on the prices of the good and the utility level that we want to attain. The higher we choose this utility level, the more units of X and Y we need to consume, and the higher the expenditures we need to make. So the first order conditions can be derived similar as before. We take the partial derivative of the Lagrangian with respect to each of the consumption goods and with respect to the parameter lambda, which gives us back the constraint that we want to obtain, a certain utility level. Now then you can rewrite again, of course, if we focus on two of these equations corresponding to good I and good J, and we take the ratio of the two, then we're back at the marginal rate of substitution. At the optimal point should be equal to the price ratio. This is just, again, the tangency rule. And we have that in the optimum, lambda should be equal to P1 over the partial derivative with respect to each of the consumption goods. How to interpret this lambda parameter? The lambda is equal to the marginal cost of utility. And how can we see that? Well, again, think of a cup of coffee. Suppose that an additional cup of coffee would give you an additional utility of 6. The price of an extra cup of coffee is equal to 2, which means that P1 is equal to 2. This thing is equal to 6. So lambda is 1/3, meaning that 1 extra cup of coffee gives you an extra utility of 6. But the price of a cup of coffee is equal to 2. So if you would increase your utility by only 1, then we need 33 extra cents, because you can buy 1/6 of a cup of coffee then, which would give you this additional utility of 1. And again, if you want to have your utility level go up by 1 util, it doesn't matter on which good you spend your extra income, because it's the same no matter which good is bought to provide this extra utility. And this, of course, derives immediately from the fact that we are considering an optimal point. We already optimized, then we get extra income, and it doesn't matter on which good we spend this extra income. Our utility will always increase by the same amount. And again, the disclaimer, this analysis only works if we are at an interior solution. Okay, let's return to our Cobb-Douglas example. So the indirect utility function we already derived before in the two-good case. And now what we can do is we can just solve this equation for the income, because the indirect utility function says okay, given prices Px and Py and given income, what is the utility that we can obtain in the optimum? And now if you solve this for income y, it tells you, okay, given that we want to obtain a certain utility level and we have certain prices, what is the income that we need in order to attain that utility level? So that is done here. We just replaced this expression here by a constant u, that is the utility level that we want to attain. And we brought this part to the left-hand side, and then we replace the income I by this functional form representing the expenditures. Now the right-hand side is in terms of the prices and the utility that we want to attain, and we make that explicit by writing the expenditure function as a function of prices and this utility level that we want to attain. So we can very easily move from the indirect utility function to the expenditure function. So we already talked about the uncompensated or Marshallian demand functions, which were optimal demand bundles as a function of prices and income. And we also have something what is called the compensated demand functions or the Hicksian demand functions. So compensated again refers to what these demand functions do. Hicksian refers to the person who has given these demand functions their name, John Hicks. And the compensated demand functions give you the optimal consumption bundle as a function of prices and this utility level, which we want to obtain. And if we substitute these into the expenditure function, or into the objective function, so we replace the x1, x2, xn over here by this expression here, then we get an expression in terms of prices and utility, and we get what is called the expenditure function. Okay, so what are the properties of the expenditure function? So since expenditure minimization implies utility maximization, in both cases we arrive at the same optimal consumption bundle. We have the following, that given that we have an income I and prices P, the indirect utility function tells us, okay, then given those prices and income, the maximum utility that we can obtain is this utility level. Then if we plug that into the expenditure function and using the same prices P1 and Pn, the expenditure function tells us, okay, given these prices and given that you want this reach this level of utility, the income that you need is identical to I. So this is the identity, and the expenditure function and the indirect utility function are each other's inverses. So just like with elementary math functions, for example, you have a function fx, and then you have the inverse function of this function fx, and the inverse is defined as, okay, if you first take the function of x, and then you take the inverse, then you are back to the original x. Now in math, one example is the natural logarithm and the exponential function. If we first take the natural logarithm of x, so this is our function of x, what is then the inverse function of this logarithm? Well, it's the function that gives you, that returns you x. So the inverse function is the exponential, because if we plug in ln x in here for y, then we get the exponent of the natural logarithm of x, which is identical to x. So this is the definition of an inverse function, and we have the same here, that if we plug in the indirect utility function, which is a function of income, then and then we plug it into the expenditure function, then we get returned the income I that we started out with. Okay, so Expenditure functions are non-decreasing in prices and they're homogeneous of degree 1. So it means that if we multiply all prices with a common factor, for example because of taxes or inflation, then the expenditures that we need in order to attain the same utility level as before, so this is our original expenditures, well, if prices say double, then we would also need to double our expenditures in order to reach the same utility level U as before. So expenditure function is homogeneous of degree 1 in all prices. And expenditure functions are also non-decreasing. It cannot be that if you increase the price of one of the consumption goods, then that leads to your total expenditures to decrease. That's something that's clearly impossible. Expenditure functions are in general concave in prices. So what does it mean? It means that if you increase the price of one particular good, then you don't need to fully compensate the individual by giving him extra income in order to make the individual just as happy as before. So to make it very concrete, suppose that an individual consumes 10 bottles of beer. The price of a bottle of beer is additionally equal to €1. So he needs €10 to buy 10 bottles of beer. Now, if the price of a bottle of beer increases from €1 to €2 a bottle, does this individual now need to spend €20 on beer in order to be just as happy as before, or does he need to spend less? So it's true that if with an expenditure of €20 on beer, the individual is able to reach the same consumption bundle as before, making him just as happy. But he will substitute away from beer consumption because it became more expensive. So instead of buying 10 bottles of beer, he will now scale down his consumption of beer a little bit and maybe buy some more bottles of wine. So taking into account these substitution possibilities, that the consumer substitutes away from the good that has become more expensive, his total expenses do not need to increase by €10, but by less than €10 in order to make this consumer just as happy as before. So what we have is that usually, in most cases, if we increase the price of one particular good, we don't need to increase the expenditures in a linear way in order to make the consumer as well off as before. However, exceptions are possible, and that brings us to the final question. So for which kind of utility function do we get that the expenditure function is indeed identical to this orange line? So for which utility function is the expenditure function not concave in prices? To give you the answer, this holds whenever the goods are perfect complements. So they're consumed in fixed proportions. So for example, if we have an economy which only consists of beer and nuts are idly consumed together, then if the price of beer increases, we can only make the consumer as happy as before if we fully compensate him or her for the increase in the price of beer. So he cannot substitute away from consuming beer towards consuming more nuts to make up for this, because they're consumed in fixed proportions, no substitution possibilities. So we need to fully compensate the consumer for the price increase in beer in order to have him or her able to reach the old utility level. So in that case, the expenditure function is linear in prices. And this brings us to the end of today's lecture. I want to thank you for your attention. and I hope to see you in good health at the next lecture.